Welcome. We're going to focus on probability intersections and unions in a two-way table. So we will be dealing with intersections, which use the word and, unions, which use the word or, specifically for a two-way table. There are formulas to calculate intersections and unions, and depending on whether an event is independent or dependent, might have an impact, whether something's mutually exclusive or not, might also have an impact. And so we will be talking specifically about a two-way table. When we are calculating intersections and unions, we have to consider what our outcome is based on, are we including everybody? Are we including too many? But first, I want to talk about what an intersection is and what a union is. Intersections are probabilities where two things intersect together or come together. It's a shared outcome. So for here, if I'm talking about probability of event A and event B, the green shaded region is what those two things share. So this is an and probability, and we also use an upside down symbol that looks kind of like a U to represent intersection as well. A union is either of the two events. And so it could be anything in event A, the intersection of what they share, anything in event B, any of that. The union, which we also use for or is another word. So intersections, they have to have the same thing in common. A union could be one group or the other group or what they have in common. So for instance, I could be in the female group and not prefer English, or I could be in the female group and prefer English. So we're trying to determine what we're calculating here. Now, intersections and unions are calculated in different ways using formulas. I will show you the formula, even though we're not going to use them for a two-way table. For an intersection, the and is calculated, the probability of A and B is calculated by taking the probability of A times the probability of B given A. And that is the general multiplication rule. If you have independent events, it winds up just being the probability of A times the probability of B. For or, we have the probability of A or B. You take the probability of A and add the probability of B, but you have to take away anything that A and B share. Now, again, if these are disjoint events or mutually exclusive that can't happen at the same time, that winds up being just the sum of A and B. But using a two-way table, it's actually a little bit more straightforward. You can just look and see where the intersection is. You don't have to multiply because you're given in the chart where they intersect. So again, we'll start with our marginal distributions. The probability of being female is 13 out of 19 total. The probability of preferring English was 11 out of 19 total. Not female was 6 out of 19 total, and preferring math was 8 out of 19. And preferring English and being a female is going to be found kind of like Battleship, where you find the row and the column meet. So preferring English and being a female, there are 7 of those. 7 people out of 19 total. We can use the same approach for English and not female. So our English preference here, and then the not female group here, where they intersect, those are the 4 that prefer English and are not female. And notice that my denominator is not changing. I'm not doing anything conditional. I'm just talking about in the group overall. Now let's focus on those that prefer math and those that are female. That intersection is 6, so there's 6 out of 13. And then those who prefer math and are not female are going to be 2 out of 19. The and, or the intersection, is found where the two come together in the chart. Or is a little bit different. To be English or to be female means I could be English or female. So all of the English people here, there's 11 total out of 19. And then all of the females, there are 13 out of 19. So if we were to just add those two together to say the probability of English, which is 11 out of 19, plus the probability of being female, which is 13 out of 19, I would have 24 out of 19. And that's too many. Your probabilities can't be over one whole or 100%. And so what's happened is, if you notice in my chart, when I counted the females, I included those that prefer English, and when I counted those that prefer English, I also included the females. So I included them twice. And that means that I need to account for that by subtracting away the difference of where they intersected. So I'm going to adjust my formula here to subtract away that 7 that they had in common. So 11 plus 13 minus 7 is going to give me 17 out of 19. The only ones that are left are these people. Use that same approach for English or not female. So preferring English, there's 11 people. And being not female, there's 6 people. But I've included the 4 English and not female group. That's going to be 11 out of 19 plus 6 out of 19 minus the 4 that I double counted. That's going to give me 13 out of 19. Now we're focusing on math. There's 8. I'm going to highlight both of these at the same time. With our female, math or female, 8 plus 13 minus the 6 that I've double counted. And the 9, and the not female has 2 that I've double counted. So let's write that out. The probability of math, that probability of math or female is equal to 8 out of 19 plus 13 out of 19 minus the 6 out of 19 they had in common, which is 15 out of 19. And then math or not female was math, 8 out of 19, plus not female, which was 6 out of 19, minus the 2 they had in common, which was 12 out of 19. That's how you find intersections and unions using a two-way table. Thanks for watching.